Good morning, my dear kids. In today's class, in the chapter Rayoptics, we are going to discuss the lens maker formula and the type of lens. It is a very small topic, so let me explain it. After this, we'll explore the application numericals on the lens, that one. So still we need a lot of theoretical background. Therefore, I'm insisting on this one. It's a very small topic, lens maker formula and type of lens. Fine. Okay, let me start the class. Okay, kids like please share my app and the website to all your friends. So it will be a helping hand for me and for all the knowledge seekers who want to enjoy the physics, unlimited physics. So this is the best platform what we are providing. So please do share to all the friends who need this app and the web. Okay, let's start the class. A lens maker formula. So already we have discussed the converging lens, diverging lens. So there are different types of lens, usually what we construct or manufacture. So how do specific focal length of a lens can be determined that one. So for that we will take a first converging lens. It can be anything. You can pick up any lens. So let me start with the converging lens. Okay, this is the thing. Okay, we have kept an object here. Let the refractive index of the lens be mu2, that of surrounding medium be mu1. Radii of this surface be r1. A real object is kept. We know the rays emitted first, the rays will undergo refraction. The ray which is incident, let me choose the red color, will undergo refraction here. So it is moving from, let's assume, rare to denser, will undergo refraction. And it finally wants to meet the optic axis somewhere here. But again, the ray will further undergo refraction and finally will converge at this particular point. So what is this? This will be some normal. This will be the normal for, and this will be the normal for this one. Okay, this will be the center of curvature C1, C2. Okay, this is the thing that one. So the ray finally, so this incident ray will undergo refraction and finally undergo refraction will meet the optic axis at a distance I. This is the object distance U. All the distance I'll measure from the optic center, so it will be P only. As is a thin lens, what we discuss is a thin lens. So our topic will be lens makers formula. Okay, that one. And this is the V. This will be V dash. So we'll have this much of thing. Okay, let's apply the refraction at spherical surface. So first at surface 1. So this is surface 1, surface 2. At 1 will apply it. And anything directed towards right will be positive because the incident ray is moving in the direction. Where the refracted ray is present in the denser medium. So what is the formula? Mu2 pi dash minus mu1 po equal to mu2 minus mu1 by pc1. Again, at second surface, this will be I dash will become image, this one, for the first surface, and same I dash will become object for the second surface. So again, let's apply the refraction here, refraction of spherical surface formula. So applying that, no. Where is the refracted ray is present in the rarer medium? Mu1 pi minus where the incident ray is present here in the denser medium. This will be mu2 pi double dash equal to mu1 minus mu2 by pc2. Radius of curvature of this. So radius of center of curvature of this surface will be here. Center of curvature of this surface will be at C1. So these are normal, sir. This is a normal. I'll write it here. We'll add up these two equations. By adding up 1 and 2, we'll get mu1 by pi minus mu1 by po equal to mu2 minus mu1 by pc1 . So here I'll move this one. Now what to do is like we have to replace these values. So as usual, this 1 by pi minus 1 by po equal to mu2 minus mu1 by mu1, 1 by pc1, 1 by pc2. So this will be v, this will be u, mu2 by mu1 minus 1. This will be 1 by r1. This will be 1 by r2. We know from length equation, this everything should be equal to all the things you have to substitute with sign. Okay, there's a basic lens maker formula. Fine. So there's a very fundamental, almost any lens you are constructing, you should take help of this particular thing. What all we discuss applicable for thin lens. Applicable for thin lens only. Okay, there's a basic formula what we have. Now using this, we'll go for the we'll analyze the different types of the lenses here. There's a basic lens maker formula. Very simple. I think you need to struggle much here. Okay, I'll take out my video. Okay, now kids, like the first lens, what will differ is a convex lens. It will be like a puri. It's a bulged one, similar to like a puri. How it will be? The lens will be a bulged one. I do have. This will be a bulged one. The lens, it will be like this. Huh? This will be a bulged one, and this will be the, so this you'll find very difficult. I'll usually will put this in. Okay, this if you want, if you want to show it, no. Usually we'll show this lens in this way. This is the thing which happens in the books. The lens is being shown in this way here. So it will be bulged. It will be like a similar to puri, pani puri, what you eat, or the bulged puris, that one. So you can see a curvature here, here. So this will be a convex lens, what we call, or a converging lens, that one. This will be the optic axis. Fine. So the refractive index, let it be mu. Surrounding, let it be A. We have to use lens maker formula to calculate the focal length. So let me assume a ray of light, and it will converge at this particular point. This should be the focus. And whenever we'll call focus, it is a second principal focus only. The radius of curvature, this be R1, R2. Center of curvature of this will be C1, this will be C2. According to lens maker formula, we have like this, no? Mu2 by mu1 minus 1, 1 by R1, minus 1 by R2. This mu2 is mu, and mu1 is 1. So what is the focal length? Will be mu by 1 into radius of curvature of this. Let R1, let this be equal to R1 equal to say R to R, anything, let it be equal to R magnitude. So substitute now with sign. R1 will be plus R. R1 will be plus R. What about R2? R2 will be negative, because how you measure the radius? Because here R1 you're going to measure in the direction of incident ray, whereas R2 you're going to measure opposite incident ray. So therefore this will become minus R. So this will become 1 by F equal to mu minus 1 equal to 2 by R, or F equal to R by 2 mu minus 1. This will call equiconvex lens. Okay, equiconvex lens. There's a special thing. Convex lens only we have brought. Equiconvex. Next, if the surfaces, radii of the surfaces are not equal, then what has to be done? Why did it not come? Oh, I'll do one thing. A second type of, in this one only, convex lens only. It is not an equiconvex. Not an equiconvex means the ray after refraction, the radii of this be R, let this be 2R. There is the incident ray, refractive index be mu, that of surrounding, let it be A. So this will be the focal length. Then this is not an equiconvex lens now. Now just you can say like a convex lens, what we can call this is. How to calculate focal length? This will be mu plus r minus of minus 2r. Why it should be like a, because the ray, what is r1? The incident ray on the surface first, on first surface on which it strikes. The incident ray will strike first this surface, no? So therefore this has to be taken, the radius of curvature of this has to be taken r1. Then the emergent ray will come from the second surface, that has to be taken as r2. Why negative sign? Because this 2r, the center of curvature, this will be center of curvature of this one. So you are going to measure this as 2r, no? Whereas this is r. And how you measure r? In the direction of incident ray. 2r opposite incident ray. So therefore this will become, okay, this will be 3 by 2r, or f equal to 2r by 3 mu minus 1. This is a convex lens. That was the equiconvex. If both the radii are equal, then it is called like a equiconvex. Okay, fine. This here radii are different. R1 is how much? I should put mod for this, huh? Not for. Okay, there's a converging lens. So like this, we can find out the focal length. So physically, it will be like a bulged disc. You can call this like a bulged disc, that one. So in a, if you see the side view, it will appear like this. That's why in the books we prefer this particular diagram. It will have the radius, this one. Okay, this is about the convex lens. Just let me adjust this one. Then we'll go for diagram. I'm showing diagrams so that it will be very easy for you. Any some good numericals they may ask you based on the three-dimensional. This is the concave lens. So if you see the, it will be spherical, but here what happen, you can easily like a saucer, cup saucer, how it will be like a, so the inner bowl. So it will be like a, both the surfaces what happen will have a bulge inward. This is what a concave lens will be. So if you see the practically, it will be, how do it will appear? It will appear in this way. If you side view will be of this kind of, the side view. This will be inner, curvature will be like this. This is a side view, what you are seeing. So then we'll go for similarly. If a parallel ray of light, beam of light is incident after refraction, this is a focal length. So there's a radius of curvature R1 and R2. Let mod R1 equal to R, mod R2 equal to R. Let this be mu. This is A. What is mu 2? Mu 2 equal to mu, this one. So what is the, there's a concave lens, huh? Equiconvex, equiconcave. So 1 by f equal to mu 1 by r, r1 will be minus r, this will be plus r. According to the length maker formula, this r1 will be positive, no? Direction of incident ray should be taken positive. So you measure R1, R1 opposite incident ray, so therefore negative, whereas R2 in the direction of incident ray. So center of curvature will be here. How you measure R1 opposite incident ray, R2 in the direction of incident ray. So therefore this will become F equal to minus of 2R mu minus 1. This is a equiconcave lens. Just only mere concave lens, only mere concave lens. So here the radii will be different. This what you are seeing is a side view. It is a side view. Okay, radii of this, let it be R, let it be 2R. The ray after refraction, this will be focal length. Different radii, there it was, radii was equal, same radii, R1 and R2. Radii are different, so how much R1? Mod R1 equal to R. Let's apply the lens maker formula. One by minus R plus 2R. So this will be F equal to 2R by 3 mu minus 1. Diverging lens. Equiconcave, just concave lens means the radii will be different. Equiconcave means the radii of the surface will be same. That one. Okay, able to understand now? So this is the, what you are seeing is a side view. What you are seeing is that there is a side view. Practically it will be like this. Okay, next we'll go for plano-convex. Plano-convex lens. I think this will be very clearly visible. Here plane surface, here you have curved surface. Or curved, this is a plane. So how we show, we just show the side view will be, it is a method of showing that one. Okay, now, so if a ray is incident, so radius of curvature of this will be infinity, let it be R, let this be mu, let this be air, let this be air. Area of light incident will undergo refraction. This will be the focal length. Okay. Now according to lens maker formula, 1 by F is equal to mu 1 by, okay, I'll run the complete formula. Some of you are finding difficult. Minus R it is. Why negative sign? R2, the radius of the center of curvature of this will lie somewhere here, no? How you measure R2? Opposite incident ray. This is the direction of incident ray. Where the radius of curvature of plane surface will be infinity. So therefore this will be mu minus 1 by R. So F equal to R by mu minus 1. This is the focal length. Plano-convex, in plenty of applications it is widely used here. Next is plano-concave. Here only will wind up. Diagrams are somewhere here. There's a plano-concave. Fourth type of lens. So how the surface will be? The inner surface, what happened? There will be like some sort of like a depth will be there here. This will be flat. This will be curved one. Okay, fine. This will be so here this will be a curved. This will be plane. So if you see the practically, it will be like side view. What you are seeing is a side view. So then this will be, so if a ray of light is incident, after refraction, it will diverge. So radius of curvature of this infinity, let this be R. Refractance as mu, let this be A, let this be A. So from the lens maker formula, 1 by F equal to mu 2 by mu 1 minus 1. It's a diverging lens. Plano-concave. One of the surface will have radius of curvature infinity. Why this will be positive? The center of curvature of this will be somewhere here. So how you measure center of curvature, radius of curvature in the direction of incident ray? In the direction of incident ray. So therefore this will be a positive. Okay, fine. So like this we will define the type of lens. So now we'll go for next the positive meniscus. Positive meniscus. This is the thing that one. Okay, now this is mu A. It's a converging lens only. It's a converging lens only. So now if a ray of light is incident, focal length will be L. Okay, now the radius of this will be, let it be R1 equal to R, R2, let this be equal to 2R. Direction of incident ray, this is positive. So applying the lens maker formula, 1 by F is equal to mu2 by mu1 minus 1 by R1 minus 1 by R2. Mu2 is mu 1 plus R plus 2R. So solving this, we'll get 2R by mu minus 1. I got positive R, so therefore it's a converging lens. Positive meniscus it is called as. I think I'll try to adjust here only. Positive, negative meniscus again. We can save place. What do you mean by negative meniscus? Next, it will be negative meniscus. Next few things like, if suppose say it is like this, there's some small information which will help you a lot. What about the position of the object? It means like position of the image. Now here is what image is formed. So this is 2R, this is R, no? If it is the same lens, now other surface faces the incident ray, where the position of image will be same. Position of image will not change. These are very small things, but for student these are very, very important. The focal length will be same. Means whether the which surface first it will strike the incident ray on which surface first it strikes, will that determine focal length? The answer is no. Hope are you able to understand? I'm trying to give some information here. In the first diagram, the incident ray will strike the surface whose radius of curvature is R. Next, here the same lens. Now if the incident ray strikes from left, or I'm showing it here now, this will be 2R. So what about the position of focal length? Will be same. So on which surface the incident ray first strikes, okay, that will not determine the focal length. Of course, here the image will be on right side. Here will be uh, like if the ray comes from this side, the incident ray first strikes 2R like this, the image will be formed here. So therefore, I'm just taking a diagram like this. Let me change let me rotate this lens. Now the surface of radius of curvature 2R face the incident ray. So where is the position of image will be same. Focal length will not change. This is very important. Negative meniscus. I do. Negative meniscus means this should be flat. First we'll do one thing. Okay, so some rough diagram may not be perfect. The radius of curvature of this is 2r. This is r. Okay, the incident, the ray will first strike the, then after refraction, will diverge from a point. This will be the focal length. Okay, now you see this. Again, the same formula. Mu 1. This will be plus 2r plus r minus 2r by mu minus 1. This is diverging length, negative meniscus. Okay, these are the six types of general, the different types of lens is what. The radii need not be 2r, right? It can be 2r, 3r, anything. Please do understand. I just took some values here, but it can be what happen any values, the radii. Okay, next if the medium on either side of lens is different. What about the focal length in that case? Medium on either side of lens is different means medium on either side of lens, let it be different here. Different means let this be mu1, mu2, let this be mu3. Then okay, now we'll send the ray of light. So many diagrams, little bit I'm not comfortable. First, the ray of light is incident here, will undergo refraction, and finally let it be here. It wants to converge here. The ray. I'll just show like this here. I think that this will be sufficient. These are the normal. So this is the incident ray, refraction, refraction. Okay, fine. These are the radii of this surface. Let it be R1, R2. First, it will strike this surface. Next, it will strike the other surface. This is I. This will be I dash. Let's get into the. This will be the focal length. V or let it be V. Later we'll call that as focal length. Object is at infinity. First we'll do one thing. At 1, what is the direction of incident ray? Towards right. At this particular point. There's an incident ray, there's a refractor. Where the refractor is present in the other medium, mu2 pi dash. Or directly you can go for the V dash. minus mu1 infinity. Because where is the object? Object is present at infinity, no? Equal to mu2 minus mu1 by plus r1. Need not to substitute this. Similarly, at refraction at second surface, towards right, the incident ray is moving towards right, so this should be positive. So mu1, this will be v minus mu2 v dash. This will act like a object for second surface. Object at infinity, image is formed at I dash. Now I dash will become will act like an object for second surface. Image is formed here. So then don't substitute any sign. We are not substituting any sign here. Adding up these two, 192 mu 3, mu 3, mu 3. Refractive index of this medium is mu 3, this is mu 2, no? I changed it. So let's add up these two. So mu 3 v is equal to mu 2 minus mu 1 by r1 plus mu 3 minus mu 2 by r2. Let v equal to f. So mu 3 by v or mu 3 by f equal to mu 2 by mu 1 by r1 . It all depends upon the mu2, mu1 values. What can be this lens, converging or diverging? So if the medium on either side of lens is different, you cannot use lens maker formula. If medium on either side of lens is different, you cannot, lens maker formula is not applicable. Lens maker formula is not applicable. That's all. It all depends. Final image, the eye can be errors. It all depends upon mu2, mu3 values. Further, this mu3, if you send, okay, let me simplify because focal length is needed, no? So 1 by f is equal to substitute r1, r2 with sign, you'll get the focal length. Okay, these are the different types of lens what we have brought it. We'll go for the combination of lenses, one more topic. Next one, combination of lenses. Just as a very simple formula is there. Let there be a two lens. How to find out the effective focal length of those two lenses? If the two lenses, if they are in combination, this is one lens, this is the other lens. Fine. So the focal length of them will be f1, this will be f2. Then I'll keep object somewhere here. First, the ray incident on the first lens will undergo refraction and wants to form the image here, I dash. But what second lens? Second lens will make it to undergo refraction. Finally, it will be a time. Now I want to replace these two by an equivalent lens so that the final position of image will not change. Let f be the focal length of, let f be the focal length of this one. The position of, final position of object should not change. And the final position of image should not change. So now so this is the U, this is V, this is V dash, this is U, this is V. Focal length of this be F1. So now what we should do? So what these two lenses, they are producing the image for the same position of object. Even this lens produces the image at same position. Then shall we say this is equivalent of these two? So now we know the formula 1 by V dash for first lens. 1 by V dash minus 1 by U equal to 1 by F1. Second lens 1 by V minus 1 by V dash equal to F2. Looking at this lens, 1 by V minus 1 by U equal to 1 by F. Let me add up these two. I'll end up with the equation 1 by V minus 1 by U. This is the equation 2. This is equation 1. Comparing 1 and 2, what we can write? 1 by F equal to 1 by F1 plus 1 by F2. Any number of lenses, even if there are n number of lenses are there, you can apply this particular formula. Then we'll go for the power. Power of lens is equal to inversely proportional to focal length, where focal length will be there in meter. Power of lens equal to 1 by F. This will be diopter, where focal length will be in meter. Then the power will become P equal to P1 plus P2. Whether lens, for converging lens, power will be positive. So what is the idea? P will be positive for converging lens, will be negative for diverging lens. This particular formula is applicable whether it's a converging or diverging lens. Both, any combination we can take help of this one. Not only this, we can go for the any combination. Like this, we can find out the effective focal length of two lenses. If two lenses are in contact, then how to replace those two lenses by one equivalent lens. So there's one basic formula is what we can apply here. Okay, I think kids like a today's class, we had the discussion about the lens maker formula. Then we constructed different types of lens. Then we went in the last, what happened? We discussed about the combination of lenses. That one, how to replace if two, three lenses are in contact. How to replace with one single lens. That one. Just have a look once. We will in coming classes we'll go for the application part. Almost I think I discussed the theoretical part completely over. In the coming class we'll discuss about the silvered lens and we'll go for all the applications. It's about only the numericals, that one. Okay, see you all of you. Take care. Bye.